Hello everyone, in this tutorial we will predict the future position of the vehicle using polynomial regression. To create the trajectory of the vehicle, we only need the history position of the vehicle and then we can predict the future position. This is really useful because if we want to avoid the dynamic obstacle, we need to know the future position of that obstacle. We can use this trajectory on any actor, not only the vehicle. Create a blueprint, actor component. Name this to motion trajectory component. Open this. In this begin play, call set timer by function name, and the function name is update history position event. Add variable. This variable is update time. Set to float. Compile. Set this to 0.1. And connect it to time and looping this event. We want to track position of the vehicle for the history position, and we want the event to tick every 0.1 second. Create a custom event. We need the same name as this name, function name. Copy this. Update history position event. And this event will call every 0.1 second. Then create a new function. Name is track actor position. Get owner. Call is valid. We need to get the owner because this is the actor component, not the actor. Get actor location. Add local variable is current position. Set variable type to vector. And set this if the owner is valid. Add variable. This variable name is history positions. And set to array. Get history position. Add this position, current position. And we want this array to have max elements. So add another variable, make history position. Set this to integer. Set to single and compile. We set this make history position to 10 because we only want this array to have 10 elements. Get history position, length, greater than make history position. And if it's greater than this history position, we add another variable, complete. Set this to Boolean. and set this complete. Get complete, create a branch. If this history position is greater than the make history position, we need to remove the first index from this. Remove index and remove the first one. It's 0. And add another boolean. Name is debug path. If we want to debug, we can set this debug path to true. Call draw debug sphere. Get current position. The radius is 30 and line color is red. Duration, we can get update time multiply with this make history position. And thickness, set this to 2. For return, connect this file to this branch, and this file we need to continue the function. Add output. Name is full array. And when the array is full, we complete this function. Go to event graph and call this track actor positions. Next, go to BPV called AI, and we add this new actor component, motion trajectory component. We want to process the vehicle so we can drive this vehicle. Get player controller, all process. In pound is safe. That actor pick enable, and we disable this event tick. Add another variable. Name this to process. Player process. And compile. Set this to true. Create the branch if we want to process the vehicle. And this event tick, we can stop this. If we set the player process, only when it falls. This begin overlap. Compile and save. Display. and we drive the vehicle. We can see the history position that we debug. We track this position and set it to the array. There are 10 positions, and we will use this history position to generate the curve. You can close Unreal Engine project and open .sln. From Visual Studio, and this is the plugin from the last tutorial that we implement the A-star pathfinding algorithm. So you can download it, link in the description below. We have to add some more function to generate the polynomial curve. The first function is static array double calculate polynomial coefficient con array double reference values in 32 and degree. This is the static function. It's a function that belongs to the class itself. This means that you can call a static function without creating an object of the class without the target reference. Static double evaluate polynomial. Cons array double reference coefficient double t, and we create u function blueprint callable category math regression static array f vector predict future position. Con array f vector reference history position in 32 degree in 32 name future points double prediction interval, and we set that default value is 1. This predict future position, we can call this from blueprint because we have this u function blueprint callable, and this function we don't need to call from blueprint. We have the history position as the vector array and the degree of the polynomial curve, number of future points that we need to predict. The prediction interval is the gap between each point for the future points. and we return the array of vector that is the future positions. Save. And in this C++ file, we need to use Eigen library. Go to Google and search for Eigen, this website. Eigen is a C++ template library for linear algebra. So you can use this Eigen 3.4, which is the latest version, and download this zip file. After we download this, we can create new folder. Name is Eigen library. Move this inside this folder and we right click extract here. Go to our project and go to plugin, algorithm, go to source, add new folder, third party. Open this folder, add another new folder is Eigen. Open this and we need to go back Eigen 3.4.0. Copy and paste it here. We can close this. Go to Visual Studio and this algorithm.build.cs. Using system.io. In this public, we add another path is path.combine module directory third party Eigen 3.4.0. Make sure the path location is the same as this location of the plugin. You can see this is third party Eigen and Eigen 3.4.0. And save. Go to algorithm bp library.cpp, then include this library. Eigen class dense and save this. We have the error. We need to clean the project and generate Visual Studio again. Close this. Go to our project and delete.vs, binary, derive data cache, intermediate, save, and .vs config.sln, generate Visual Studio project file. Open Visual Studio. Open this game, plugin, algorithm source, and open this algorithm BP library. You can see that this includes Eigen doesn't have any error anymore. So our math is correct. Before we write any code, I would like to introduce a little bit of math for you for easier to understand. We have two graphs. The first one is linear model, which is the straight line, and the second one is polynomial model. And this point is the history position of our vehicle, and we can generate this curve along this point, which is the best fit curve. So we have this equation. This one have only x, and this one x squared, which is more degree than this equation. And this is the mathematical formula. Y equal to beta 0 plus beta 1x plus beta 2x squared plus beta 3x cubed plus 2 beta n xn. This beta are the coefficients. We need to solve for this beta. The degree of the polynomial is the highest power of x. If we have x squared, it is the second degree polynomial. And if we have x cubed, it is third degree polynomial. And we get this equation. We can write it in metric form. If we multiply this metric with this beta metric, we get this equation back. And this one, we can represent this by A metric. And we use QR decomposition to solve for beta. A equal to Q, or Q is orthogonal metric, or is upper triangular metric. And we get this equation. You don't need to care about this equation because when we use Eigen library, we can solve this by using only one line of code. A.householder.qr.solve y. And we get this result as coefficients. After we get this coefficient, we can represent this curve by the equation. And we use this curve to predict the future position of the vehicle. Go to algorithm bp library.cpp. We copy this function, scroll down and paste this, delete this static, use algorithm bp library. In 32 and equal value dot name. If n less or equal degree, we print the log temp error x not enough data point to fit the polynomial of the desired degree and return array double empty. Eigen matrix HD A n degree plus 1. This is the row and the column of the matrix. Eigen vector HD B n. For in 32 I equal to 0, I less than n plus I double t equal I b I equal value for in 32 j equals 0, j less than equal degree plus j. A ij math over tj. This part we initialize both of these metrics. Eigen vector HD coefficient equal to A dot householder QR dot solve B. We use this function to solve for coefficient. Array double coefficient array for in 32 I equals 0, I less than coefficient of size plus I coefficient array dot add coefficient I. After the for loop, we return coefficient array. We convert this vector x variable type to the array, and then we return this coefficient array. Go to this header file and copy this function. Delete this static. New algorithm BP library. Evaluate polynomial. To evaluate the equation, It means that we substitute the variable into the equation and then calculate the value. Double result equal to 0.0 for int 32 I equal to 0, I less than coefficient dot name result plus equal coefficient I multiply with f math over ti and return the result. When we evaluate polynomial, example, if we set x to 2, we set this to 2 and this one to 2, and we already have the coefficient. Then we calculate this y value. Copy this. New algorithm BP library. Delete this static. Here double x value. Here double y value. For cons f with the reference position, each of the history position. We add to x value and y value array. Add position dot x y value, add position dot y. We only calculate x and y because we don't need z. Our vehicle drive on the flat plane. Here double find the coefficient of x, calculate polynomial coefficient, x values, and degree of the polynomial. Here double y coefficient, calculate polynomial coefficient, y values, degree. Here f with the future position. For int 32, I equal 1, I less than or equal to 5 future points plus I double future index equal to history positions dot name. Subtract with 1, add with I, multiply prediction interval. Double future x equal to evaluate polynomial x coefficients and future index. Double future y equal evaluate polynomial y coefficient future index. Double future z equal to 0. We assume that z is 0. F vector future position equal F vector of future x, future y, and future z. Then we add these two arrays. Return future position. Here we have the history position and the degree of polynomial, number of future points, and prediction interval. And we get this future position from evaluate the polynomial of the coefficient that we calculate. Let's save and we run this. We get an error because this C++ function, we set this to 1. Prediction interval without any equal. We can only set this in header. And so let's run again. Open BP vehicle AI. Motion trajectory component. Now we can call predict future position. This function, we don't need the target like this function. So we can call this in any actor. Get history position. Add variable degree and choose integer. Compile. Set this degree to 2. If you set this degree to higher, it can overfit. So the curve can capture too much noise from the vehicle positions. Add variable, make future position. Compile and set this to 10. Add variable, future positions. Vector, change to array. Set to array. Get future positions. Call for each loop. Break vector. Make vector. Connect x to x, y to y. Get owner. Get actor location. Split this. Connect C. We do this because our future positions that we get from this predict future positions, the value is 0. And get future positions, set array element. Set this index, this item. And get debug path. Create a branch. Copy this, draw debug sphere. If it's true, we draw this debug sphere. Set to green. And this location as the center location. We need to set this make future position. We can set this to 10. Let's play. Now our vehicle have the future position trajectory. Create another blueprint. Actor. BP. Dynamic obstacle. Open this and add a cube. We choose this MI solid blue material. This cube, let's set the scale x to 5, y to 8, and z to 3. And the location is 150 for z. Go to event graph and set. We have to make this obstacle moving. Add another variable is path boolean. Get path. Create a branch. Get actor location. Add variable. The variable name is actor location. And set the variable type to vector. Subtract this with actor location. Get actor right vector. Call dot product. If this false, create a sequence. Add variable movement range and set this to float. Compile. Set this movement range to 1500. If it's greater than this movement range, create a branch. And if this less than this movement range, create a branch. Add another variable. Add or subtract. Call boolean. If it's true, we set it to false. If it's less than movement range, we add it back. And this sequence, we create another branch. Add or subtract. Get actor location. Add with actor right vector. Multiply by the speed. Convert this to float. We can set the speed to 30. Next to add. Then call set actor relative location. If this true, we add to the right vector. And if this false, we add to the left vector. Multiply the speed by -1. Then we can add the motion trajectory component. Because this dynamic obstacle only move in a straight movement, so we can change this degree to 1 to create a linear model. It is more accurate. Drag this to our scene. In begin play, we need to set actor location. Get actor location and set to this actor location. We multiply this movement range to -1. Compile and save. Let's play test. And now you can see that this bug move forward and backward. We have this future position prediction. Next, we want to spawn the bug at the position of the future position. Go to BP, dynamic obstacle, viewport, add bug collision. Set this bug extent to 250, 400, and 150. The location is 150. It's the same size of this bug. And we can set this line thickness to 5. Search for hidden in-game. We can set this bug collision hidden in-game to false. Create another blueprint, actor, BP, force field. And add bug. This bug collision. And set this line thickness to 5. Go to motion trajectory component. Create another custom event. Name is found force field. We need to add another variable is bug collision. Set this to bug collision. Object reference single. Get bug collision. Check if it's valid. Get make future position. Subtract with 1. Call for loop. Last index. And the first index is 0. Next, we spawn actor from class. Split this, spawn transform. Select class, BP force field. And we set owner. Get owner. Set to this owner. Add variable force field. BP force field. Object reference array. Get this force field. Add to the array. We get bug from this force field. Set bug extent. Get bug collision. Get bug extent. Set this in bug extent. Add variable debug force field. Set boolean. Set to single. Create a branch. If it's true, we set this bug hidden in game to fall to make it visible. If it falls, we set hidden in game to true. Add variable is force field. This one is force field with S, and this one is force field. After we spawn this complete, we set force field boolean to true. Next, we add another function is update force field. Get box collision is valid. Get future position. For each loop, if this valid, we add another local variable array index integer. Set this array index. If this array index greater than 0, and get future position, get a reference, this index subtract with 1, and copy this. We use this array index. Distance, get owner, get actor location, connect to this distance greater or equal to 200, and connect to n boolean. Then we create a branch. Get force fields, get a copy, get array index, call set actor location and rotation. If it's true, we get this array element location, break vector, make vector, x to x, y to y, get box collision, get world location, and split this, connect Z to Z, and connect to new location. Then to get the rotation, we get unit direction from this index subtract with 1 and this array index position. Create a rotation from x vector get box collision get world rotation, find delta rotator, and combine this rotation. Break this vector, make rotator, connect yaw to yaw, and then connect to this rotation. Next, we need to set actor location and rotation. When this is false, we want this position when it doesn't move very much. We want it to set to default value. And this location, the rotation we get from get owner, get actor rotation, break vector, make rotator, and connect this yaw, connect to new rotation. Now we have the update force field location and rotation. Go to event graph. When this set array element complete, we call get force field. If it's true, we already spawned this force field. So we need to update the location and rotation of this force field every tick. And to get this bug collision, we need to compile this force field. And this one we compile and we don't have any error. Go to BP dynamic obstacle. We have this bug collision that is the shape of the cube. Get bug and get motion trajectory component. Set bug collision. And this trajectory called spawn force field. Because we want to use this bug extend to set to the bug of the force field to have the same shape. Next, we set this debug force field to true. To set this hidden to false. Let's play. Now you can see this bug collision spawn and update with the position, future position of this bug. You can change this, make future position to spawn more position, or if you want the gap of the bug to be bigger, you can change this prediction interval. Let's try change this future position to 5 and change this prediction interval to 2. Let's play. You can see we have less future position, only 5 position, and the gap between each point is bigger than before. Set back to 10 and this one to 1. Let's try it on BPV called AI. Create a sequence. Get motion trajectory component. Set box collision. And we use this box collision. You can see this is the box collision of our vehicle. And then call found force field. Let's play test. And we have the vehicle that have this box found. When we stop, the vehicle don't move too much. That box will set to the default rotation of the vehicle. It's similar to how the trajectory from the motion matching predict the motion, but we use only position. We don't use any physics to predict it. You can disable this debug by disable this debug path and this debug force field. When we play, we don't see this. Go to BP dynamic obstacle and click on this box. For hidden in-game, set this to true, because we don't want to show this to the player. This is the end of our tutorial. We already create the prediction for our vehicle using polynomial regression. Thank you very much for watching. If you like this tutorial, please hit like and please subscribe to my YouTube channel. Thank you very much for my patrons member who are supporting me. Your support really means a lot to me. See you in the next tutorial.